So I'm Brittany. Doug Montgomery and Sarah Burke are my co-advisors at ASU, and my dissertation focuses on optimal designs for multi-response experiments. So we use optimal computer-generated designs when a standard design doesn't fit the problem. And although there are usually multiple performance and quality metrics that experimenters are interested in, much of the research in designed experiments focuses on one response. And there is relatively little research done to address multi-response experiments with responses that follow different distributions. You can keep talking. We're good. So this leads to the primary problem statement for my research, which is to provide a general solution to finding a design for multiple responses that follow different distributions. And to demonstrate a solution, we consider a three-response problem that involves a normal response with continuous data, binomial, such as detection or survival of a target, and a Poisson response, which models count data like number of false alarms. So if you look at the optimal designs for each of these individual responses, there are some differences. So these are d-optimal and Bayesian d-optimal designs in the case of binomial and Poisson. With 16 runs, the replicates are labeled where they occur. So if you have these three responses in an experiment, which design should you choose to run? Well, if you have unlimited time and funding, you could run all three. But if runs are expensive, or you really just want to maximize the information that you get for all three responses from one experiment, choosing one of these, there's going to be trade-offs. If you pick any one of these designs, the models for the other two responses are going to suffer. So using a weighted optimality criterion, we created essentially a hybrid design, which ends up being a better choice for all three responses than any of the individual optimal designs. So I do want to point out, you put a weight, W sub N, B, or P, on each of the responses, which is assigned ahead of time. And the optimality criteria are calculated in the algorithm. And the algorithm is going to search for the design points that maximize the overall weighted optimality criterion. But common challenges associated with a weighted optimality criterion include choosing the weights and then interpreting those weights. So equal weights on the response variables doesn't necessarily imply equal interest, which leads to a secondary problem statement, identifying a method for finding optimal weights when using a weighted design criterion. So by requiring that the weights on the responses sum to 1, we can treat them like components in a mixture experiment. And with 3 responses, you can use a ternary plot to view all of the possible weight combinations and see that equal weights, which is that triangle in the middle, is just 1 point on that plot. But we can use a space-filling mixture design that's going to spread design points throughout the design region, which offers an efficient way to explore different weights in the criterion. So that's very high level. And if you want more information, you can stop on my poster.